Okay, so today we're going to start a new lecture set, so that's kind of cool. We're starting lecture set number 5, which is on cluster sampling. So I'll give a little bit of an introduction to cluster sampling momentarily, and then we'll effectively be working through the same practices that we talked about before. So we're going to talk about estimation of the population mean, estimation of a population total, estimation of a population proportion. We'll talk about some of the expected properties of the estimator, though in this particular unit, we are going to focus more heavily just on estimation. For the most part, cluster sampling works in a very similar way to simple random sampling, except how you treat the units of interest is quite different, which is what separates the two. So like with the stratified approach, it's really more of a conceptual the differences really lie in how we're collecting the information, but I'll give some more insight into this momentarily. I'll just go through the usual reminders here. So we have, today is the 17th of March, which I guess I should have written in green since it's St. Patrick's Day. So today is March 17th, 2021. So we have quiz 3 on March 29th, which is a Monday, March 29th. That's going to be post stratification through lecture set 4, and I still have to post the exact slide numbers for that. I will do that. I haven't forgotten. I've just been pretty busy. And then assignment 4 is due on April 9th, I believe. I'll just confirm that real quick. Yes, on April 9th. And assignment 4 has been posted. So this is, assignment 4 has some questions about cluster sampling, some questions about two-stage cluster sampling, which are things that we'll talk about in this lecture. And it also has a few questions, or one question about ratio estimation within stratification. So it's kind of a bit of the last parts of lecture set 4 that we didn't test on assignment 3, and lecture set 5, which we're starting today. All right, one other announcement. So on Friday, we're not going to have a live lecture. We're going to have an asynchronous lecture. So I will post a video before Friday, and that video will essentially just be a lecture like the one that we regularly have. So I'll also post a reminder about this on Blackboard, but the idea here will be that we don't miss any time, and you can use that video in the same way that you would use this video. So or this live lecture section. So I would suggest just watching it on Friday morning at 9 and using that time as you would to attend the class. And that lecture will cover, starting from wherever we finish today up until, about 50 minutes from that starting point. So it'll be the same duration, the same style. It just won't be a live lecture Friday at 9. But again, I'll send a reminder about that. Okay, so with all that being said, let's start talking about what cluster sampling is and how we can utilize cluster sampling, the estimates from cluster sampling, etc. All right, so we're actually going to talk about 2 types of cluster sampling strategies in this lecture set. So we will have the traditional cluster sample, and then we will have the 2-stage cluster sample. So the first half of the lecture, or maybe the first 3/4, is devoted to the traditional cluster sample. So the traditional cluster sample is very similar to a simple random sample, but the difference is that instead of sampling individual units, you are sampling collections of individual units. So with SRS, we would sample individual observations, or we can just say people, just to make it more clear. But with the cluster sample, we will sample collections. of observations. Okay. And that could be something like a household. Right? So one of the benefits or one of the reasons that we would be interested in using cluster sampling would be that well, compared to stratification, would be that the cost of obtaining a sampling frame could be very high for each of the different strata that we have split the population into. Further, we might be interested in using cluster sampling when the cost of collecting information from each element in the population increases as the elements in the population get further from each other. So those are just a couple of examples of when you might be interested in this approach, at least compared to the stratified approach. Because again, as a reminder too, with the stratified approach, you are also breaking the element into different regions, right? So you would have, for example, if you considered Alberta, you might break it into the 5 different sectors like Edmonton, Calgary, and then north, central, west, or north, central, south, for example. But with cluster sampling, it would be a similar idea, but then within each of those sectors, you would be sampling, again, collections of households rather than individual households. Okay, so to illustrate the idea, let's work through the following scenario. So we have researchers want to investigate the average income per household in a large city. So if we use simple random sampling, you would have to have a detailed frame listing all of the elements that in the city, which could be very costly. And then from simple random sampling, so say that you have some large city like, I don't know, Toronto or Vancouver or something like this, and your frame gives all of the households in the city, so a list of every single household. You can imagine how large that sampling frame might be. When you go to select the random sample from the frame, so as a reminder, the frame is our list of all the elements that are available to us, and our sample is going to be just a selection of individual elements from that sampling frame. So when you go to select all of the units from the sampling frame, you might end up with a situation where the units are scattered maybe as far apart as they could be across the city. So, while that might be more representative because you're kind of collecting from all the different regions of the city rather than getting focused into individual parts, that would also be very costly because you have to travel to or contact all of those different units. I mean, now you might make the argument too that in the modern era, this wouldn't really be as much of an issue because of, for example, email and electronic communication. But you could imagine that if that wasn't an option, it could potentially be a very time consuming process and a very costly process to travel to each of these very far or potentially well spread out households to collect information. Okay, if we use stratification, what would happen now is that you would break the city into your different strata. So you can imagine if you have sort of a very dense city, let's say that we broke it into, I don't know, 5 strata just for illustration purposes. So you now have your city divided into these 5 different strata. Actually, maybe I'll illustrate this here. Okay, so this box could be, for the SRS case, this could be the city. Let's make it a nice clean box. Okay, so this could be the city, right? And let's also just say that this is also the same thing as the sampling frame. So we have the list of everything in this city just for illustrative purposes. So I'll just write also the sampling frame. So from SRS, like maybe you end up with something like this where everything is just really well divided. And then we would say that the cost of attaining information from all of those different points are, so the cost of obtaining information from the different households that were selected is going to be high just because of the dispersion of the households. All right, now say that you have the same representation below, but we're in the stratified case now. So in this illustration, okay, so it's the same definitions as before. So we have our city or the sampling frame. But now what you've done is you've kind of broken the city up into different strata. Okay, so here, well, maybe we'll just use 6 strata, just again for illustrative purposes. So this could be strata 1, strata 2, strata 3, strata 4, strata 5, strata 6. All right, so now maybe you collect a few observations from within each of the strata. So these are randomly selected values now. Okay, so the nice thing about the stratified approach compared to the simple random sampling approach, maybe I'll just add a few more points here, just, for consistency. So with the simple random sampling approach, the issue we run into is we have to travel to each of these different households individually or contact each of these different households separately. So we have to go to the first one, and then travel to the second one, whatever, move to the third one. In the stratified random sampling approach, we've broken the city up into these different strata. So now let's say that we pick 6 strata, just again, arbitrarily. You then collect an SRS within each strata, because that's essentially what stratification is. It's a division of the region of interest into its different sectors. And then within each of the different, it's a division of the region of interest into the strata. And then within each of the strata, you collect a simple random sample. So we have our simple random samples within each of the 6 strata that we have sketched out. If you have a person assigned to each strata, that's going to be much easier for them to contact each of the randomly selected households because they're in that region. The only thing that's wrong with, or the only thing that is that the stratification approach doesn't solve is the issue with the sampling frame. So you would still require the same sampling frame for the stratified approach that you would for the SRS approach, because the frame doesn't change. You're just dividing the frame into different regions. So with cluster sampling, and we'll see if I can illustrate this in a meaningful way, but it'll be more difficult, I think. Okay, so with cluster sampling, we have the same idea. So here's our city. Here's our sampling frame. So with cluster sampling, what we're saying is rather than selecting the households directly and then asking them the questions that are of interest to us, we could use, for example, blocks of households or neighborhoods, for example. So collections of different households as the sampling unit. So for example, I guess let's say if we took like a similar image to what we had before. So suppose we considered again the stratification approach. All right. Well, it's not technically going to be stratified, so we wouldn't have to do this. But let's say we took the idea from the simple random sampling. So we returned to the simple random sampling sketch where we kind of had our observations spread out randomly like this. Okay. So now what we would be saying is rather than target the individual households separately, we might target, for example, blocks of households. So let's say, just for illustrative purposes, that this is like one block, and then over here we have another block, and then maybe this can be its own thing. And then over here we have another block. So now each of the red collections become the sampling units. So we're randomly selecting this whole group of blocks at a time. Okay, so this is the unit for our sample, and then we can collect information from each of the blocks rather than go to each of the individual households. So the reason that this is beneficial, first, you can kind of see that compared to stratification, the idea is you've almost created regions, even though you're not actually directly separating the frame into different regions. You're kind of just collecting observations together. But that in some sense kind of serves the same purpose, because if you think about, for example, a city layout like the one that we are using in this example, when you go to collect the blocks, you're kind of in some sense stratifying based off of the different blocks in that city. Or if you were to treat neighborhoods in the city as the sample and then collect information from each of the neighborhoods, which wouldn't be a completely unreasonable way of approaching something like average of approaching a problem like estimating average income. If you were to use the neighborhoods, you're sort of stratifying based off of the neighborhood anyways, but just not in the same way that we would with stratification. So that solves the one problem in terms of transportation and contacting the units, because you now have these different neighborhoods and you can assign someone to each neighborhood, for example, or to each block, for example. The reason that this is beneficial from the frame point of view is because now you don't actually need a list of the different households, you just need a list of the different neighborhoods or blocks that are within the city. So that would reduce the size of the frame as well. Okay. Any questions? Okay, so cluster sampling again is going to be beneficial because it reduces the size of the frame, so the complexity of the sampling frame, or it can potentially reduce the complexity of the sampling frame. And it can also be useful because it can make collecting information easier, since you can target the different clusters within the sample. So city blocks are, again, an example of clusters that are typically used within different surveys. So for example, on slide 5, I have a few different illustrations of this idea. So local governments sample city blocks to plan new transportation methods and housing developments. So again, instead of targeting individual households, they target collections of households. The US Census Bureau report block statistics for all urban areas with populations exceeding 10,000 people. Market research firms use block statistics to determine if there is a market for a new product or store in an area. And churches use block statistics to locate optimal sites for expansion. So things like this. Okay. So again, the units in cluster sampling do not have to be individual persons. They can be collections of persons. So for example, a car is a cluster containing 4 tires, which could be used to estimate tire wear and safety. So you can gain an estimate from the one car rather than having to sample each tire individually. The same way you could gain an estimate from a household that is composed of, say, 4 people, instead of sampling each person in the household individually. All right, so one of the natural questions that comes out of cluster sampling, or when you want to conduct a cluster sampling type analysis, is how many clusters do we actually need to use? So there is no good answer to this question. It really is a situational answer, so it depends on what it is that you're trying to do. But the rules for constructing the clusters are very similar to the rules that we use for constructing strata. So you'll notice in point 2 here, okay, so we would like the elements within the cluster to be highly correlated, and we would like the elements between clusters to be very different. So that way, when we use an individual cluster, the average value that we get out of that cluster would be representative of all of the points in said cluster. And then we would like the different clusters that we do utilize to be well separated so that we're getting a better representation of the entire population. Okay. And again, this is very similar to stratification, right? So we would compare to definition of strata, right? And this goes back to the point that I was trying to make a little bit earlier when we were looking at the illustrative example of the different city blocks. So you have these clusters and you have the strata. And what you're hoping to gain from the clusters and from the strata is pretty much the same. You want strong correlation within and differences between. So you want the clusters to be in different locations, the same way you want the strata to be in different locations, so that you're not overestimating a particular portion of the population. But the benefit of cluster sampling compared to the stratification approach is that you have a reduction in frame complexity, because the frame is now composed of the collections of units rather than the individual units themselves. Okay. So again, there's no good rule for choosing the number of clusters. We can do, and we will see some sample size style calculations based off of variance for selecting the number of clusters, but it depends on the situation and the complexity of the population that you're dealing with, right? So the diversity of the population that you're dealing with. All right, so estimation. So cluster sampling, as I said at the start, is effectively just simple random sampling, but it's simple random sampling where each sampling unit contains a number of different elements, right? So as we saw before, just with the little illustration, right? So if we have an SRS, this is going to have our points kind of like this, and each of these are individual points. But then if we consider a cluster sample, we're basically just selecting regions instead, and then there's all the points within the region. Okay, that would be our cluster sample. All right. Now, with that being said, the amount of notation and the number of different variables that we have to keep track of in cluster sampling is much more complicated, or instead of using the word complicated, I would say the list of variables is longer for cluster sampling than it is for simple random sampling. So when we use cluster sampling, we let capital N donate the number of clusters that are in the population. All right. So again, if we consider this box to be the frame, okay, so we're going to say we have capital N clusters. So this could be 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So here we have, say, capital N is equal to 9 different possible clusters within the population. Okay, little n is the number of clusters that are selected. So say that we like took this one, this one, this one, this one, and this one. So now we have little n is equal to 5. Okay, so we've randomly selected 5 of the 9 possible clusters. Little m underscore I is the number of elements in each cluster. So little mi is the cluster size. So what we would be saying here, for example, would be something like m1 equals 15. So that would mean 15 elements in cluster 1, right? And then maybe we had m2 is equal to 27. That would mean 27 elements in cluster 2, right? So capital M, I'm just going slightly out of order for a moment here. So capital M is going to be the total number of elements in the entire population, okay? So we let capital M be population size. Okay, so the notation is slightly different. So N, which we are used to being the value that represents the number of observations in the population number of observations. In the cluster sampling scheme, the little n and the capital N represent the number of clusters. So in that sense, it is consistent with the definitions that we had for the simple random sampling approach, because for the simple random sampling approach, we let capital N and little n represent population size and sample size. Here, well, we let little n represent the number of units we selected from capital N. With the cluster sampling scheme, the units are collections of values. So little n still represents the number of units that we have selected from the population size, but the units are now these collection of values. So we let m, small m, represent the number of values in the number of elements in each cluster. Capital M is just the total number of elements across the whole population. So capital M in cluster sampling was capital N in simple random sampling. Then we also have average cluster size. This is the standard definition. So the average cluster size is just the number of elements in the population, so capital M, divided by the number of randomly selected clusters, right? So this would be little m bar is going to be, we can call this little m. Actually, I'll just leave that one as it is, just to not overcomplicate it. But you can see little m bar is the average cluster size across all of the selected clusters. Capital M or capital M bar is the average cluster size for the entire population. So this here would be the sum across all clusters of the cluster sizes divided by the total number of clusters. And then yi is the total of all observations in the IF cluster. So this yi here, this is the response value. Okay, so that's actually what we're measuring, depending on the situation we're looking at, but we'll see some examples of this momentarily. Does anyone have any questions at this point? All right, so when we use cluster sampling, again, we're gonna have the same goals that we usually have. So we're gonna wanna estimate a population mean. We'll wanna find the variance of our estimator so we can bound the estimator. We might wanna estimate a population total, and we'll see population proportion as well. We're actually gonna study the estimation of the mean and the total in two different scenarios. So this would be the traditional scenario. So you can see here that the form of the estimates is pretty much exactly what you would expect. So you have mu tilde c is equal to the sum of the yi. So again, the yi is the response value. So this is the total response value across each cluster divided by the sum of the mi. So the number of observations that were used across all of the sampled clusters. Okay. Now then you can see we have the variance of u tilde c. This is 1 minus n over capital N. So notice that our FPC is in terms of clusters. Right? And then we have sigma hat squared for the cluster divided by n, so the number of sampled clusters, multiplied by m bar squared, where again, m bar squared is average cluster size for population. Okay, when we look at the form of sigma hat c, you can see that this is the sum across the number of selected clusters. Okay, again, little n represents the number of clusters of the yi, so the value for each cluster, minus mu hat cs. Okay, so these are all, I'll just call this mu hat c. Mu hat c multiplied by mi, so the cluster size. So this thing actually looks like a ratio estimator. So this has the form of a ratio estimator. Okay, and we'll return to this idea in a little bit. So, and if you think about this, this is somewhat logical because you're basically saying the sum of the average multiplied by mi. So you are weighting the average value from the cluster by the size of each cluster. So you're kind of accounting for that when you multiply the, or divide by the, subtract the mean. Okay. If we do not know capital M bar, then we can estimate it using little m bar. Okay, so we can replace capital M bar here with little m bar. So this average size of the sampled number of clusters if this is unknown. Right. Okay, and then estimation of the total is going to follow from the same logic as before. So basically, we're going to take the, sorry, 1 sec, let me just confirm something here. That is definitely. Yeah. Okay, and then estimation of the total is going to follow in the same way that it did before. So basically, we're just going to say the estimate of the total is equal to the estimate of the mean from the cluster sampling approach multiplied by the total number of observations within the population. Okay, and this is basically the same definition that we saw in the SRS case and the stratified case, even for ratio estimation. We're just multiplying the mean by the total number of observations within the population. And then if we apply that to the variance, we end up with m squared outside. Wait, sorry, 1 sec. So this would be m squared over n squared. Oh, no. This is supposed to be an n. Sorry, this is supposed to be an n. Yeah, that makes sense. Because you have m bar squared here. So that would be m over capital M. So the capital M's would cancel out, and then you have the n squared, yeah. Because this part here, sorry, I'll just go through what I was saying, I'm trying to say. So this part here follows because you would have m squared multiplied by the variance of mu tilde c, right? So that would be what we would expect to see. But then the variance of mu tilde c is m squared multiplied by 1 minus little n over capital N, sigma hat c squared divided by little m. And then you have here capital M over little n all squared. Okay. And then you can see what's going to happen here is the capital M's are going to cancel out. So those divide out. And then you have little n over capital N squared. So the capital N squared comes up in front. So that's what this is, the correct form. Yeah. I'll just say since here. Since this is equal to that, then that's true. Okay. This becomes n squared. Well, I don't need to write that part out, but it's clear. Okay, cool. Any questions? Does that make sense? All right, so let's look at an example now. So we have cluster sampling is used by a manufacturer who wants to estimate the average repair cost for the saws he sold to certain industries in the past month. So we have 20 industries. We have the number of saws sold per industry or sold to each of the different industries. And then we have the total repair cost across all of those different saws. So let's just start by breaking down what we actually have here. so that we can understand the problem. First, the goal here is to estimate average repair cost. So the repair cost is the variable of interest. So this here, the total repair cost, this is yi, which is the variable of interest. Right, and then we have the number of, well, then we'll have industry. So the industries here, this is going to be the number of clusters. In sample. Okay, so the industry is going to be the little n. So we've randomly selected 20 clusters from capital N clusters that this person has actually sold saws to, which in part B we can see as 96. Okay, so we'll talk about that a little bit more once we get there, but the idea is we sampled 20 from 96 industries. Okay, so the number of saws are going to be the units sold to each cluster. So this is going to be the M subscript I. Right, so we have, from the initial declaration, we have little n is equal to 20. We have little m is equal to 130, because you can see in the table we're told that the total number of saws that were sold is 130. For each of the different industries, we have the number of saws that are sold. So little m is the total number of saws sold, so that's 130. And then we also have the sum from I equals 1 to little n of the yi, which is equal to 2,565. So the total repair cost is the variable we're measuring. So that's the y subscript I for the cluster sample. So the total here represents the sum of the repair costs across all of the selected clusters. All right, so in part A, we want to estimate the average repair cost per cluster using cluster sampling. So from our declaration on the previous slide, we're going to have mu hat C is equal to the sum from I equals 1 to n of the yi divided by the sum. Actually, I should write that in the proper way. So this second total, which I called little m, I mean, we could just call it little m. I'll call it both. This is little m, which is the sum from I equals 1 to n of the mi. Okay, and this is the sum from I equals 1 to little m of the mi. So that's going to be 2,565 divided by 130. Right, and that gives us 19.731. Right, so it's a pretty straightforward estimation process. The only tricky part is just making sure we understand what's being presented to us in the problem. So again, here we're letting the number of industries be the selected clusters. We're letting the number of saws would be the number of elements per cluster. So that's our MI. And then the repair cost is what we're measuring. So that would be the variable of interest, which is our YI. Okay, in part B, we want to do our usual 95% CI. So we would start off by computing our variance, and then we would use that to bound our estimate. Okay, so you can see here that we have a declaration that capital N equals 96. So this means that we sampled 20 industries from 96 different industries. So the person that's interested in estimating average repair cost, he sold saws to 96 different industries and then randomly sampled 20 of those industries and took the total repair cost from each. So we have here the variance of mu tilde C is equal to n squared, 1 minus little n over capital N, multiplied by sigma hat squared C, divided by little m little n times m bar squared. Okay, so for the finite population correction, we're going to have 1 minus 20 over 96. So it's pretty obvious that this is going to have to be applied because that's certainly not going to be larger than 0.95. And then for the m bar, we don't have capital M. Okay, so it's always spacing issues. All right, so here we can say capital M is unknown, so use little m bar, right? Okay, so this is going to become 96 squared multiplied by 1 minus 20 over 96 multiplied by sigma hat c, which is going to be 845.5607. Right? And then that's going to be times 20 multiplied by m bar squared, which is going to be 130 divided by 20 squared. Okay. And that should give us something in the area of 0.792. Okay. So therefore, the 95% CI is going to be given by 19.731 plus or minus 1.96 multiplied by the square root of 0.792. Okay. And then, I mean, from here, we should be able to work it out pretty easily. So that will be 19.731 plus or minus 1.745. Six to 21. All right. Any questions? Oh, yeah. Good call. Good catch. Thank you. All right. Any other questions? Okay, so if, as we saw in this illustration, particularly for part B, We did not have capital M, so we were not able to, or we had to use little m bar rather than capital M bar in our equation for the variance of the mean estimator. If we want to estimate the total and we do not have M, an alternative estimate can be found through, or simply by essentially replacing capital M with capital N. Okay, so in the absence of capital M, we can say that tau hat is going to be equal to capital N multiplied by what we call mu tilde t. So this is simply just capital N over the sum of the variable of interest divided by little n. So this would be also a traditional estimator in some sense, or the form of kind of the traditional tau estimator, right? But you can see that the differences here are that we're using only the cluster sizes. So we have capital M, capital N, and little n, and the sum of the yi. So we're not dividing the sum of the yi by the sum of the mi in this alternative. So when capital M is unknown, we can use tau tilde given in equation 3. And this takes capital N and multiplies by the sum of the yi over little n. And then our estimate for the variance changes to be equal to n squared times the FPC multiplied by sigma tilde squared t, or sigma squared t, where sigma squared t is effectively just the deviation of each of the clusters, or each of the totals from the clusters minus the average of the total, the average of the variable from that cluster. So this is a more traditional sort of estimate of the variation in the variable of interest around each of the different clusters. So for example, in the previous illustration, suppose that we wanted to estimate the total amount spent on repairing the saws, but we do not have capital M. So we can use the information given in equation 3 to find these estimates. So again, the idea here is we do not have capital M. So we can say, for example, tau tilde is equal to capital N over little n multiplied by the sum from I equals 1 to n of the yi. So that's going to be 96 over 20 multiplied by 2,565. Okay, and that gives us 12,312. Okay, and then if we want to bound this, so we'll say the bound is equal to 1.96 multiplied by the square root of the variance of tau tilde. All right, so this is going to be 1.96 multiplied by the square root of 96 squared, 1 minus 20 over 96 multiplied by 6,908.618 divided by 20. And that's going to be equal to 3,111.567. Okay, so that's an introduction to cluster and sampling. So this is the fourth simple systematic stratified cluster. So this is the fourth sampling scheme that we've seen in the class. Again, you can see that simple random sampling is effectively the foundation for all of these different schemes. In so far, what we have seen is the idea or the rationale for wanting to use cluster sampling. And then we have shown how to compute the mean from cluster sampling and how to compute the total. And an alternative for finding the total when the total number of elements from the population of interest is unknown. So in Friday's lecture, which again will be an asynchronous lecture, we will continue to work through lecture set 5, and we will finish at wherever the time limit takes us. So as always, if you guys have any questions, please let me know. I will post some reminders about the recap for the week, what we have covered, the way that Friday's lecture is going to work, what's on quiz 3, and all that sort of stuff. Hopefully by the end of today or the end of tomorrow. And otherwise, I won't talk to you in person until Monday. But yeah, if you have any questions, let me know. And otherwise, have a good rest of the week and a good weekend.